Good evening, dear President, past presidents, Professor Priyan Dias, our guest speaker today, council members, members of the ISL, family members of late Engineer Dr. A.N.S. Kulasinghe. You all are welcome to the 14th A.N.S. Kulasinghe Memorial Lecture. This is the first time we are going to have this online. However, there are some key people present here, except for President, who is unable to come all the way from Kandy, though he wishes to come in. Other than that, we have here Professor Priyan Dias, our guest speaker, Professor Ranjit Disanayaka, Chairman of the Civil Engineering Section Committee, past President Engineer Chula De Silva, who accompanied Dr. Kulasinghe's son, Mr. Upul Kulasinghe. So as one of our very senior members who happen to be here, Mr. Engineer Karnara. So to start with, I cordially invite following dignitaries to light the oil lamp, starting from Engineer Chula De Silva, past president, to represent President ISL, and also the past presidents. Engineer Professor Priyan Dias, our guest speaker today, a family member of Engineer Dr. A.N.S. Kulasinghe, that is Mr. Upul Kulasinghe, who is present today. Engineer Professor Ranjit Disanayaka, Chairman Civil Engineering Section Committee ISL, and Neela Pesek, myself. Thank you very much. Now I respectfully invite Engineer Chula De Silva on behalf of the President ISL, Professor SBS Abayakon, to garland the photograph of late Dr. Kulasinghe. I kindly request you to stand up. Yes, please. Thank you very much. Kindly be seated. I invite Professor Priyan Dias and Professor Ranjit Disanayaka to the stage. As per the agenda, next item is to welcome, delivering the welcome speech by the President of IESL, Professor S.P.S. Abeyakon. We have allocated him only 5 minutes, but he insists that he needs a minimum of 10 minutes because he has a lot to say about Dr. Kulasinghe. Over to you, sir.
Thank you very much, Engineer Labesekara. I hope you all can hear me well. I regret very much my inability to be there on this extremely important day for all of us. And I thank those who are there for coming there so that these initial rituals can be performed as we do every year at this important lecture. Good evening, ladies and gentlemen. One of the most distinguished scholars of Sri Lanka, Kumaratunga Munidasa, once said, "Alut alut daya notanina jatiya luwa nonagi," meaning a nation that has no innovations will not rise in the world. The great theoretical physicist Albert Einstein said, along similar lines, "Imagination is everything. It is the preview of life's coming attractions." In Sri Lanka, ladies and gentlemen, in the sphere of engineering, I cannot think of a superior innovator than Deshabandu, Vidyajothi, Arumadura Nandasena Silva Kulasinghe. Past presidents of Institution of Engineers Sri Lanka, distinguished invitees including Mr. Upul Kulasinghe and other members of the family of Deshabandu Vidyajothi A.N.S. Kulasinghe. Today's invited speaker, Senior Professor Priyan Dias of University of Moratuwa, members of the Council, fellows and members of the Institution of Engineers Sri Lanka, ladies and gentlemen. We are gathered here today to honor this great son of Sri Lanka, who is the undisputed father in modern civil engineering construction in this country. I'm certain that Dr. Kulasinghe has earned local and international reputations that are unparalleled by any other Sri Lankan for his innovative practices of engineering. I would like to welcome you on behalf of Institution of Engineers Sri Lanka for this very important annual event. Born in Udamita Jayala on 26 October 1919, Dr. Kulasinghe had his education as English Boys College Vaduwa, Maristella College Rigambu, and St. Benedict's College Kottayam. At St. Benedict's, he carried away first prizes for physics and mathematics throughout his period, and in the last year there, 1938, he was also awarded the first prize for Sinhala and coveted gold medal for general professions. I have noted that his own character is summarized in what he has written in an article he prepared for St. Benedict's College Millennium magazine in the year 2000. As an advice to the young Benedictines, he wrote, I quote, "Consider why you are sent to school by your parents and why you are attending school. It is not only to learn the various subjects and pass examinations, but also to become citizens of good moral character, so you can unselfishly serve your community and country. Concentrate on the task before you and do not waste your time. Do not try to change society till you are mature enough to understand and appreciate the problems in life. For ideologies, change with maturity and experience." Unquote. In 1936, while being a student at St. Benedict's, young Kulasinghe got himself enrolled at the Ceylon Technical College to study for the BSc Engineering degree at the University of London, winning the Sir Sri Chandrasekhara Scholarship. He started his long and illustrious career as a technical assistant at the Northern Bridge Hydropower Project in 1940. He joined Colombo Harbour as an assistant engineer in 1944 and gained the associate membership of the Institution of Civil Engineers London in 1946. He was appointed as the Assistant Harbour Engineer Maritime in 1947, and in 1949 he introduced pre-stressed concrete to Sri Lanka. This is considered as one of the major contributions of Dr. Kulasinghe to structural engineering in this country. He was appointed as the Chief Assistant Engineer and Deputy Chief Engineer at the Colombo Port Commission in successive years, 1956 and 1957, respectively. Dr. Kulasinghe's passion for combining research and innovations with the practice of engineering led to his establishment of Hydraulic Research Laboratory and Structural Engineering Research Laboratory at Colombo Port Commission in 1951 and 1953, respectively. His thirst for knowledge in both theory and practice continued throughout his life with his innovative construction techniques. Some of his contributions, such as the use of reinforcement cage of Mahavali Mahasaya in Kotmale to fix the shuttering for the superstructure, are truly amazing innovations. Ladies and gentlemen, during the period of Cold War, although Sri Lanka was a member of the non-aligned group of countries, we were offered several industries by the socialist countries, mainly Soviet Union. These offers were different from some of the other offers we receive today, as they did not have strings that are detrimental to the country attached to them. On the contrary, Soviet Union, in offering industries such as the steel factory at Orwell and tire factory in Kalania, insisted that we establish a state-owned facility for construction activities of the factories. This resulted in the birth of State Engineering Corporation in 1962, with Dr. Kulasinghe as the founder chairman. Dr. Kulasinghe was also the founder chairman of the Central Engineering Consultancy Bureau, National Engineering Research and Development Center, and Sri Lanka Association of the Institution of Civil Engineers, UK. He was the president of Institution of Engineers Sri Lanka in 1969-70 session and the president of National Academy of Sciences in 1987. He is a fellow of countless number of academic and professional bodies in Sri Lanka and abroad. He was awarded doctorates from University of Peradeniya, University of Moratuwa, and the Open University of Sri Lanka. He also served as the Chancellor of the Open University of Sri Lanka. Among other contributions, Dr. Kulasinghe pioneered underwater pile construction and dynamic testing of piles in Sri Lanka. In his 80s, also, he was into his innovative work, and he was instrumental in developing a very effective and innovative process of producing biogas with household waste. Ladies and gentlemen, in the history of Institution of Engineers Sri Lanka, more often than not, one of its annual functions, be it the annual general meeting or a day of the annual sessions, fall on the birthday of Dr. Kulasinghe, 26th of October. He had a habit of organizing social gatherings at his residence in Jayala for fellow engineers after the event, complete with traditional music and traditional food. For a very long time, this was an event that was cherished by the engineering community of the country. They were looking forward to the opportunity of associating their well-respected guru in the profession at this pleasant social setting in Jaya. I'm very happy that the lecture today is delivered by one of the very eminent academics produced by the country, Senior Professor Priyan Dias. Selection of the speaker today is quite significant, as Professor Dias is also a distinguished structural engineer of the country, and also as he has won the Kulasinghe Award for the Best Civil Engineering Graduate at the University of Moratuwa in 1980. At a time when the country is developing plans to revamp the economy after the COVID pandemic, the topic of today's lecture, extending some Kulasinghe innovations, is both informative and timely. I thank the Civil Engineering Sectional Committee of the IESL for organizing this event in an exemplary manner, especially considering the current situation in the country. At a time when innovation is the need of the hour, holding this important event, overcoming many difficulties, in itself is the least we can do for the great inventor, Dr. A.N.S. Kulasinghe. My sincere gratitude is extended to two eminent senior engineers, Engineer W.M. Jayawardena and Engineer Gamunu Silva, for providing me with some unpublished information on Dr. Kulasinghe. I also would like to inform you that a reprint of Kulasinghe Felicitation Volume, Innovation and Self-Reliance, originally authored by past President Engineer D.L.O. Mendis, will be available at the IESL within 1 week of today. This was made possible by generous contributions of a few senior members of the Institution of Engineers Sri Lanka. Thank you very much.
Thank you very much, President. Now we have a small video clip to be played. I have wanted to inform earlier that this was prepared by the Civil Engineering Sectional Committee, headed by Engineer Manjula Samarsinghe, who was supposed to be the MC today, but due to the situation in the country, he was not in a position to come in. Thank you very much, Engineer Manjula Samarsinghe. There again, I have forgotten to introduce Madam Dias, who wanted to witness Professor Pian Dias' speech today. You are also welcome to the ceremony.
Engineer Dr. A.N.S. Kulasinghe was born on October 26, 1990 in Mudamita, Jahala. Receiving his primary education at Wadhu English Boys College, he later moved to Nigavo Morrisella College and then to St. Benedict's College, Kotahina, where he completed his advanced level examination. He then went on to obtain Bachelor's of Science in Engineering at the Ceylon Technical College. Setting off as a young professional of the country, Engineer Dr. A.N.S. put his engineering career in 1940 by joining the Ceylon Hydroelectric Scheme for the Norton Bridge project as a technical assistant to the chief resident engineer. In 1944, he joined the Colombo Port Commission as a junior assistant harbour engineer. He obtained the prestigious corporate member status of the Institution of Civil Engineers London in 1946, followed by the fellow membership status of both the Institution of Civil Engineers London and the Institution of Mechanical Engineers London in 1957. He was promoted as the Chief Engineer of the Colombo Ports Commission in 1963 and was later made the Port Commissioner in 1968. The Kulasinghe CPC system of pre-stressing concrete is among one of his greatest, most progressive contributions made towards modern construction technology. Engineer Kulasinghe was an avid inventor, owning a number of inventions to his name, including a 30-ton garbage recycler, concrete bolts, and arch-shaped asbestos roofs, to name a few. In 1960, his invention in pre-stressed concrete went on to win the President's Prize awarded by the Institution of Engineers, India, for the best new invention. The trend-setting engineer transforming the Sri Lankan building construction industry went on to serve as the founding chairman and the general manager of the State Engineering Corporation. Some of the iconic structures designed by engineer Kulasinghe includes the Kalutara Bodhistupa, Colombo Port Stupa, the Planetarium, and the Mahavali Mahastupa. Engineer Dr. Kulasinghe was appointed as the president of the Institution of Engineers Sri Lanka in 1969. In 1979, the University of Moratuwa conferred onto him the degree of Doctor of Science. Then again, he was conferred the doctoral degree in engineering by the Open University of Sri Lanka in the year 2000. Engineer Dr. Kulasinghe is the founding leadership behind many of the reputed scientific and engineering organizations in Sri Lanka, including the Sri Lanka Commission of Inventors, Central Engineering Consultancy Bureau, and the Center for National Engineering, Research and Development. For his remarkable contributions made for the advancement of local engineering and construction sector, he was accoladed by the national honor of Vidyajothi by President J.R. Jayawardena in 1986. He was also awarded the title Deshabandu by President Chandrika Kumartunga in 2005. Engineer Dr. Kulasinghe is a living example and was a firm believer that the Sri Lankan engineers are second to none in their talents and capabilities to undertake a project of any complexity. His death at the age of 87 years in 2006 deprived Sri Lanka of one of her greatest, pioneering, most influential engineers. However, the name Vidyajothi, Deshabandu, Engineer Dr. A.N.S. Kulasinghe will echo in the heart of Sri Lankan engineering community in generations to come.
Now, to introduce today's guest speaker, Professor Priyan Dias, I cordially invite another professor, Professor Ranjit Sanayaka, Chairman of the Civil Engineering Section Committee. Thank you, Neil. Good evening, everybody. It is my great pleasure to introduce today's guest speaker, Professor Priyan Dias. Professor Priyan Dias graduated from the University of Moratuwa in Sri Lanka, 1980. He's just not an ordinary graduate, but he was the winner of the Kulasinghe Award for the best civil engineering graduate. Later, he obtained a doctoral degree in concrete technology from the Imperial College, London, in 1986.
Before becoming a senior professor in civil engineering in University of Marathwada, Professor Priyan was the research fellow at the Institute of Complex Engineered System, Carnegie Mellon University in USA. And also he worked at the Department of Civil Engineering, University of Bristol in UK. He also the head of Department of Civil Engineering of University of Marathwada from 2007 to 2010. And the director of Office of the Research of University of Marathwada from 2014 to 2017. Ladies and gentlemen, he has made contribution to the knowledge in disaster resilience, especially after the tsunami 2004 in tsunami Lodi, and concrete technology by promoting the use of fly ash and the offshore sea sand in Sri Lanka. He is as a consultant, he has given a lot of assessment of the structures in the industry. He is the associate auditor of the Journal of Civil Engineering and Environment System. To his credit, he has published over several books on various topics in engineering, titled Philosophy for the Engineering, Practices, Contents, Ethics, Modules, Failures. And graded example in concrete design, and was the co-author of IOC UNESCO Guideline 52 Tsunami Risk Assessment and Mitigation for the Indian Ocean. Professor Priyan Dias is a fellow of Institute of Engineers since 1998, and his contribution to the various academic and non-academic activities of the Institute. He is also the Sri Lankan representative for the Institute of Structural Engineers, UK, and the current president of the National Academy of Science of Sri Lanka. Sir, over to you.
Thank you for that introduction, Professor Sanaika. I will have to address people in the audience here as well as those listening online, and hopefully you can all hear me properly and things like that. So let me start by saying President IESL, who is with us remotely, Professor Abekon, Civil Engineering Sectional Committee Chairperson, Professor Ranjit Disanaika, past presidents of IESL, including Mr. Chula Disula, who is here in the audience, Mr. Upul Kulasinghe, who is a member of Dr. Kulasinghe's family, Executive Secretary IESL, Neela Besekara. I need to thank the IESL and especially the Civil Engineering Sectional Committee for giving me this opportunity to deliver this memorial lecture. Now, of course, the word innovation I have used in the title. I think it is clear from all the speeches that have gone on before, including the video, that Dr. Kulasinghe was an innovator par excellence. The extent to which his innovations can be extended is probably limited, and I sometimes wonder whether in delivering this lecture I am sort of echoing the saying which says fools rush where angels fear to tread. But I will talk about some of the innovations that I hope to talk a little about in terms of developments that have taken place, to which I have been able to make some modest contributions. Before doing that, normally it is customary for an orator at one of these lectures to establish some links with the person who is honored by the lecture. So as you can see in this slide, which perhaps is not very clear, but I don't intend you to look at every detail in the slide. It was a great honor for me to be asked by the editor of the Sunday Observer, to write this appreciation for Dr. Kulasinghe soon after he passed away. He gave me very little time to do it, and I was able to do it because a few years earlier, the Society of Structural Engineers had asked me to write a citation when it bestowed an honorary fellowship on Dr. Kulasinghe. So I was able to make use of that to write this appreciation, and I will read parts of it. Deshabandu Dr. A.N.S. Kulasinghe bestrode the stage of Sri Lankan engineering practice over the past half century like a colossus, quite in contrast to his diminutive physical stature. He is a household name in our country, a feat rarely achieved by engineers whose indispensable contributions to society are almost always shrouded in anonymity. He demonstrated pioneering leadership and remarkable ingenuity in many fields of engineering, displaying a virtuosity that is hardly ever seen in these days of ultra specialization. Then I'm not going to read the whole appreciation, but towards the end, there are certain things that I refer to which are reflected in this slide. In 1979, Dr. Kulasinghe endowed the University of Moratuwa with an award in his name for the best civil engineering graduate to be presented at the annual convocation. If memory serves me right, I think I was probably the first recipient of this award. And this is the certificate that I was able to fish out from, inside my cupboard. And it was a great honor for me because actually at that convocation, that was a convocation when Dr. Kulasinghe was awarded an honorary doctorate also by the University of Moratuwa. Later on, I say in this appreciation recently, that is around 2006, when the university decided to convert such awards to gold medals, he responded again with a generous contribution despite his ailing health and attendant expenses. I had the great privilege of meeting him as it happened just 3 days before his demise to thank him in person. I still have a copy of the check. I have blocked out the amounts because I did not want it displayed in public, but his signature is there, as is his signature on my copy of this book called Innovation and Self-Reliance, which he autographed just 3 days before he died. So now you can see, as a result of such contributions, we give gold medals like this. This particular gold medal is a gold medal won by Isuru Nanayakala, who features in 2 or 3 of the slides that I'm going to present, 2 of them actually. He was one of the best students at Moratuwa University had produced, and I had the great privilege of him working under my supervision. Let me continue reading this. I said, I remember, as I recall, his movements were slow, but his mind as agile as ever at 87 years of age, and still focused on his 3 main areas of interest as I saw it during that conversation. He was anxious that I see for myself his pre-stressing exploits embodied in some factory buildings that had been erected in record time. So the third slide from here, I will talk a little about one of those buildings and what transpired after that, of course. He bemoaned the fact that engineers were reluctant to design shell structures and felt that at least our engineering faculty should commission such structures. In the next slide, I'm going to talk a little about shell structures. Finally, he was concerned that research institutes, and also that be staffed with those having a genuine interest in research, and also that university academics who do have such interest are exposed to engineering practice. And we're going to talk about that in the second slide from now, where they would find a rich vein of problems to tackle. He spoke also of his 2 engineer sons far away in Aberdeen, but very supportive of his inventions and patents. His wife, probably his most ardent supporter, predeceased him by almost 20 years. Now, there is one other thing before I leave this slide, that is a list of these past president of the Academy of Sciences of Sri Lanka. And Dr. Kulasinghe was one of the early presidents. The reason I give this slide is so that I can have some kind of connection with him, because I happen to be the current president. By this, and by some of the remarks that I have made, I am in no way saying that I am following in the footsteps of Dr. Kulasinghe, because I say at the end of my appreciation, his was and is a hard act to follow. An engineer's son parade, as the IESL felicitation volume describes him, an engineer without equal. May his life and work be an inspiration for us to try. So if at all, these are just modest attempts look at some of the subjects that Dr. Kulasinghe was interested in. So first of all, we have the idea of shell structures. Now, our most ancient structures, in the Anuradhapura period, they were of course not shell structures. They were solid structures made out of brickwork. The Jetavana, I think at one time was the tallest brick structure in the world. Here also, I think Dr. Kulasinghe was involved in some of the restoration works, not of the Jetavana, but of the Mirisavati Adagata. And there was some controversy about that as well. But anyway, the first time we see vaulted structures where we have brickwork or stone spanning a certain distance like this is in the Polonnaruwa period. So this is a vaulted structure. But fast forward many years from there, and we see now this Kalutara stupa. This looks like the Jetamanarame here, but actually it is a shell. And devotees can actually go inside the stupa to perform their various religious observances. So this was a great innovation by Dr. Kulasinghe. Just this morning, I think in both the Daily Mirror and the Island newspaper, Sir Cyril Dusavisa is mentioned, and Dr. Kulasinghe's erection of this stupa is mentioned in this morning's newspaper. Then, of course, it was mentioned earlier on about this Mahavali Mahasaya. And the great innovation there is that the formwork, the reinforcement itself was used to support the formwork that formed this shell structure. And then, of course, there is this folded plate structure in the Colombo Planetarium. Now, I have to confess that I have not constructed any shell structures or not got anywhere near to constructing shell structures. But some of the research, like I said, done by Isrona Nakkar in the recent past has been on thrust network analysis. And this has to do with looking at shell structures that will be in compression alone. So a typical shell structure will have compression in some areas, tension in other areas, and those can be well accommodated by reinforced concrete structures. But if we have shell structures with only compression, then we can use a whole new range of materials and also very low-cost materials like brickwork and even clay, because such materials cannot take tension. So thrust network analysis is a computational system where we have a form. I mean, this is a typical shell, a part of a typical shell, and we can discretize this, something that engineers do, into various components like this. If every node on this surface has only 3 branches meeting at it, then what we call the force diagram will be made completely of triangles like this. So as you can see, this is a familiar triangle of forces, and we can solve for the forces in this part of the structure quite easily. And we can do this for the horizontal direction because this is a projection onto the horizontal plane, and we can do it in the vertical direction as well. So let's sort of go down from 3 dimensions to 2 dimensions because it is a bit easier to understand. So we can think about a 2-dimensional arch here. An arch just has 2 dimensions in the y direction vertical and the x direction horizontal. So think first of the arch being in this configuration, where it is symmetrical about this y-axis, a vertical y-axis. Then, of course, you have all the forces on the arch, primarily the self-loads of the arch, all acting vertically downwards. And we can discretize this arch as shown in this blue line here, different segments of the arch. Each one of those segments will have a triangle of forces as represented here. The larger triangles represent actually the end reaction here, because this will be parallel to this end reaction here. This will be the horizontal thrust experienced at that point, and this is half of this vertical load that is applied at this point here. And similarly, this other triangle will be for the other edge. Every one of these different segments will have its own triangle of forces, but they will all lie on this single line. In other words, we are able to use this thrust network analysis only if the forces acting on it are all parallel at the same time. Now, the extension that we did to this work, or largely Isuru did to this work, I must say, is to accommodate horizontal forces like seismic forces. So if you apply a seismic force, it means that it is a horizontal force. how do we apply a horizontal force and still get all the forces to be parallel. Now you can think about it by thinking that this arch is going to be tilted a little. So from this position, it gets tilted to this position. And now it is symmetrical, not about this y-axis, but about the y-dash axis, right? But gravity, of course, continues to act vertically downwards. So parallel to this symmetrical axis, we will get a component that will be g cos lambda. And perpendicular to this, we will get a component that will be g sine lambda. Now we can switch this back so that this is acting vertically downwards, and then this will become a horizontal force. The important thing that we get from this tilt analysis analogy is that the horizontal force will be a fixed ratio of the vertical force here. So what we have is, instead of these blue thrust lines here, we now have these red thrust lines. In this case, we will get a vertical force downwards, horizontal force in this direction, and all these lines going through each one of these points will be parallel to this arrow like this. So this will be the triangle of forces that we have, and then we can find all these forces. So the trick is to be able to find the thinnest possible arch that can accommodate both these lines simultaneously. So then we can get an optimum solution for this arch. So this is the two-dimensional problem. Now there are two ways that you can do it, two ways of optimization. One is if you use what is called a least squares error solution. Here we think about the difference between this line and this line in the y-dash direction, and we try to minimize it. In this one, what we have done is we have looked at the errors at every point in a direction perpendicular to the arch axis. So in the direction of the arch thickness. So you can see that this one gives a better solution. There is a thickening of the arch at the base here in order to accommodate both lines expeditiously. And in any case, we know that arches are thickened at their supports because they have to take bending moments and things like that there. So if we put all of these things together, we can come up with some kind of design chart like this. Where here we have a rise upon span ratio. So that means you can have arches of different geometry. A low rise upon span ratio means it will be a very shallow arch. A high rise to span ratio means it will be a very steep arch like this. We have different horizontal acceleration coefficients. So if you go along this rise upon span ratio and choose which horizontal acceleration coefficient you have, it will meet another family of lines in this picture. I don't know whether you can see, it's in green, and that will give you the required thickness of the arch, in this case something like 0.08 meters, 80 millimeters. So this is a small experiment that is carried out to indicate that with this kind of thickened arch, that we can reach angles of tilt that are quite significant. So you can see this is not taking any tension because this is made of every individual block. You can see all the blocks collapse, meaning it cannot take tension. But even though it cannot take tension, it can take a considerable amount of tilt, or in fact horizontal load. So these are the places where what we call hinges form. Any arch can have 3 hinges and still be stable, but it cannot have 4. So projecting onwards, if we can think of very free form structures like this. Here we talked initially about a shell like this, then we reduced it actually to a very simple 2-dimensional arch. But now we can go for any free form structure, and we are able to represent that form like this, draw our form diagram like this, convert it to a force diagram, and we are able to solve various problems like this. So this is a small contribution to shell structures from a research point of view. So let me move on. Right. One of the research areas that Dr. Kulasinghe was involved in, especially at the NERD Center, was the use of rice husk ash in cement. So broadly speaking, rice husk ash falls into those group of materials called supplementary cementitious material. Now, this slide actually has been perhaps in preparation for maybe around 35 years, because there is information from about 35 years that I have included in this. So the chairman of the sectional committee also said that he was involved in the use of pulverized fuel ash in cement. So I was involved in this even when I was doing my doctorate at Imperial College. And more recently, after the coal power plant was established in Puntland, there are at least 2 cement companies in Sri Lanka that use coal power, the fly ash from that. It is a byproduct of the coal industry, and they use it to supplement their cement production, to substitute part of the cement with this supplementary cementitious material. So what is happening here? Whether you have rice husk ash or whether you have pulverized fuel ash, they are both waste products from a given industry, one agricultural, the other industrial, right? So the use of a waste material obviously is going to bring ecological benefits. It is also going to bring energy benefits, because instead of using 100% of ordinary Portland cement, if you use 70% of Portland cement and a material that has already been produced, then that means you are going to use less energy. And the world is facing an energy crisis. But more than that, even the production of 1 ton of cement also releases 1 ton of carbon dioxide into the atmosphere, not only through the chemistry of cement production, but also through the burning of fossil fuel in order to produce that. So once again, if we, instead of using 100% cement in a given mixture, if we use only 70% and use 30% of a supplementary cementitious material, then we are once again contributing to ecology, right? So we are partially replacing the cement with these supplementary cementitious materials. So I'm going to focus now more on the fly ash. And fly ash, are made of spherical particles like this. Their shape is spherical. So this is a scanning electron microscope image. Now a cement particle is about 100 microns wide, maybe about 1/10 of a millimeter. But these fly ash particles are much smaller and spherical like this. So there are 3 or 4 things that happen when you mix this fly ash with this cement. For one thing, there is dilution. There are various things that cement particles do that are not always beneficial. For example, it emits a lot of heat during hydration. And there are various reactions that are not very attractive in cement. For example, it is susceptible to chloride intrusion and also to sulfate attack. So those effects are diluted by including this supplementary cementitious material. The cement particles gain strength when the water reacts with the surface of the cement particle. Now, sometimes these cement particles can tend to stick together, but if smaller particles go in between them, they get deflocculated. So it exposes the surface of the cement particles for the hydration to take place. Because these particles are circular in shape, it creates a ball bearing type of effect and makes a concrete mix more workable. So that's called a thixotropic effect. And also it fills in the voids, causing the whole structure, the concrete matrix, to be more compact, and also less water to be used in the production of cement. And if you use less water, the concrete will have higher strength. Above all, it has what is called this pozzolanic effect. So these are the calcium silicates in the cement, which react with the water and produce calcium silicate hydrates. This is the strong component in the cement. This is the rather weak component, the calcium hydroxide. Now, if you have supplementary cementitious materials, they are able to react with this calcium hydroxide and produce more calcium silicate hydrates. So you can see here after 112 days, because this pozzolanic reaction takes place over a long time, we can see that these fly ash particles are being attacked, perhaps by the calcium hydroxide, and they are producing more calcium silicate hydrates in this kind of way. So these are some of the benefits. There is increased strength and reduced porosity because of this additional calcium silicate hydrates. Then, like I said, when cement hydrates, there is an increase in the heat of hydration. So there is a lot of heat that is generated. So this is a lab experiment that was done now maybe about 20 years ago. This is how if you have ordinary Portland cement, the temperature will increase. But if you have 25% fly ash, the temperature rise is reduced and also the temperature, maximum temperature takes place a bit later. So it is generally better. So when the Lotus Tower was being constructed, the base of this foundation was 2.5 to 3 meters thick. And it was a no-brainer that we would have to use PFA, 25% PFA. That was the mix that was available in order to concrete this so that the temperatures could be kept below 70 degrees or whatever number it was at that time. So there is increased strength, reduced heat of hydration, then resistance to chlorides and sulfates as well. So if you, because there is less amount of cement, then the susceptibility to chlorides and sulfates is reduced because the amount of cement is diluted. So one of the ways that the chlorides are responsible in marine environments for the corrosion of the reinforcement. So normally there is a layer of concrete between the surface and the reinforcement, but the chlorides can get close to the reinforcement through this ion exchange process. So the chlorides exchange for an OH ion. But if you have less OH ions, as is the case with the fly ash mixers, then the rate of progress of these chloride ions is less. And also the porosity, like I said, is less. And therefore the chloride ingress becomes less for that reason as well. And so there is resistance to chlorides and sulfates. So when the Lotus Tower was coming out of the ground, there was discussion as to whether we needed to use fly ash anymore. So our Professor Nanakar at Muratu University and I were involved in this, and we said resoundingly, yes, we must use fly ash even above the ground level, because this is in a marine environment, here the Pereira Lake, and here we had 25% fly ash used in the superstructure as well as in the foundation. And then finally, the Chinese contractors themselves, when they had to pump concrete to this great height, they wanted even more fly ash, which we readily agreed, 37% of fly ash, because there is better workability, better pumpability of the concrete. Now, where fly ash is concerned, there are some concerns. There is some reduced carbonation resistance, but this is very, very small. And one of the things that we need to do with fly ash concretes is perhaps to make sure that they are cured better. And also there can be some plastic shrinkage cracking because of the closed structure of the fly ash concrete. The bleeding is reduced, and so the time for the evaporation to exceed bleeding will reduce with the increase in pulverized fuel ash. This is another experimental setup that we had at Muratu University, and these tests were done many years ago. Now for some of the new developments in PFA, before I go there, this is some samples from my Imperial College days. So I used fly ash there also. We were looking at the effect of, well, actually creep of concrete at high temperatures. But while we were doing that, we were heating concrete to various temperatures. Well, these were actually neat cement paste specimens. So this is a specimen heated to 375 degrees and then cooled back to room temperature. This is to 400 degrees C and cooled back to room temperature. There is a big difference between this 25 degrees centigrade. Now this one is completely cracked. That is because at 400 degrees centigrade, you have dissociation of calcium hydroxide. When it cools back to room temperature, it is rehydrated by atmospheric moisture, and then the rehydration causes expansion that causes cracking. Now, this is the same thing here with 0% PFA, but even with 10% PFA, you can prevent this cracking of the cement after exposure to temperatures in excess of 400 degrees centigrade. So, some of the newer things that are being done here, which once again we have done in our laboratories, now the use of nanosilica together with this fly ash and this cement. Now, why do we need nanosilica? Because now the intention is to reduce the ill effects of cement production. So instead of using just about 30% of fly ash, can we use 50% or even 70% of fly ash? So if you use such large percentages of fly ash, then of course your performance will go down. And one of the ways that the performance can be bumped up again is to use small amounts of nanosilica. So we can see that the envelope can be pushed further by using small amounts of nanosilica in combination with larger replacement percentages of fly ash. The other thing is just a small table here indicating the way that we value the contributions from this. So, for example, now everything has to come down to costs in the end, whether they are energy costs, ecological costs, or even financial costs. So I just want to say that, say, for example, if you look at the ecological cost, right? So how many kilograms of carbon dioxide have been emitted for 1 kilogram of cement? That's a question that people who are concerned about global warming should be asking. So for the pozzolanic cement, so this is a particular type of cement that was developed in Curtin University in Australia, with which I had some involvement. So here we have this figure of 0.43 for the pozzolanic and 0.89 for the OPC. So it is 1/2 of the cost if you compare it kilogram for kilogram. But actually we should not be comparing it like that. We should be comparing it not only on the basis of 1 bag of cement or 1 kilogram of cement, we should be comparing it on the basis of what kind of strength can be achieved by that cement and what kind of duration can be experienced by a structure that has that cement. So these are performance-based cost indices. So this is kilogram carbon dioxide per cubic meter per megapascal per year of use. So here we can see that the pozzolanic cement actually is 1/4, not just 1/2, 1/4 of the OPC. Of course, this is exposure or service life in a marine environment. So I think I have covered all that. Just to say that this is a picture of Lotus Tower. The team from Monaco University were involved in its construction, for which I'm very happy to have been involved in. So it looks a nice iconic structure, but more than that, I'm telling you now, it is a poster structure for the use of PFA in concrete. So if any of you are thinking of building anything near the coastline, make sure you use at least 25% PFA in your mixers. So time to move on. How do I go to the next slide? Okay, here we go. Right. So this is one of the pre-stressed concrete structures that I had to look at, constructed by Dr. Kulasinghe. Unfortunately, it was a structure where one of the girders had collapsed. Now, the girders had collapsed not due to any fault of Dr. Kulasinghe, but there is a story that arose out of this, and that is the story that I want to say, because it is an area that I have been making some kinds of contributions to knowledge in this area. So this is the Putlam cement factory, and this is called the gantry crane yard, where all these raw materials are stored, and of course there is a crane that ferries it from one side to another. Now this is the kiln where the cement is produced, and this is the crusher where I think the limestone and things like that are crushed. Now it so happened that one night, one of these girders, so these girders were about 100 feet long. They are made of segments like this, A, B, C, D, E are all cast segmentally, separately, and they are all post-tensioned together by this kind of curved tendon like this. So that was a method of construction that was popularized by Dr. Kulasinghe, because you can post-tension it all down at ground level and lift it up to this very high elevation. So then these structures, of course, so two of these girders, there were purlins in between them, and there were roofing sheets on top of these purlins. So the reason this collapsed was because about 150 millimeters of cement dust had accumulated on the roof, because the kiln precipitator of the cement factory was malfunctioning, right? So cement dust was spread not only on this roof, but all over the countryside when we went to inspect it, right? So, of course, that is why it collapsed. On looking more closely at some of the other trusses or girders that had not collapsed, we suspected that if at all there was a weakness, it was a weakness in the shear capacity of these post-tension girders, right? Now the question is, like I said, there was no design error in this. It was a design due to misuse, right? The question is, as designers, are we better able to improve our craft so that we make our designs idiot-proof. Idiot-proof against idiot constructors and idiot-proof against idiot users. I'm not saying the cement corporation managers were idiots, maybe they just didn't have any money, but still it was not used in the way it should have been. So this is a picture of the design process. So in the design process, we come up with some solutions, say maybe this kind of post-tension girder. We analyze it for different load cases. We make an evaluation against the specifications, make sure it has enough strength and enough, and it just does not deflect so much. And then we send it out to fabrication. We operate it, and then we can make some diagnosis. So this post-construction diagnosis is what is called learning from failures. So the 20th century was dominated, the philosophy, the discipline of the philosophy of science was dominated by a philosopher called Sir Karl Popper. So Karl Popper's view of science was that science had never reached its end point. But every scientific theory needed to be falsified so that science could make more progress. So which is why we saw at the early part of the 20th century, Newton's theories were unable to explain the wobble in the orbit of Mercury, and which is why Einstein's theory took pride of place. So every time there's a scientific theory, in fact, Popper advocated that we try not to prove our theories by our experiments, but we try to find situations where our theories will fail. Because it is only when our theories fail that science progresses. Now, as engineers, of course, we cannot build structures in order that they fail so that we can learn from it. We cannot do that. That's not the way we build structures. But whenever there are failures, then we need to grab the failure with both hands and ask, is there some part of this onion of engineering practice that we can improve? And so you see, this is the onion, the kernel of the onion is engineering science. I think by and large, we have learned most of what we need to know in engineering science. During the time of Galileo, they made some mistakes in this, but engineering science, there are very rarely failures due to engineering science. But there could be failures due to idealization, due to the margins of safety that we employ, due to the design philosophy that we use, sometimes due to the design context, and then due to the engineering process itself. I'm not going to go into all of these, but I want to highlight this particular failure. Now, this failure is of a building called Ronan Point in 1968 in London, on the outskirts of London. Now, what happened here was that there was a gas explosion early in the morning on the 18th floor of this building. It blew out the walls of that particular floor because these the walls were actually carrying the loads of the floors above. All the floors, which were precast walls and precast slabs, fell onto the 18th floor slab. That slab was unable to take that load, and therefore that collapsed the walls and the slabs below it until all the kitchen areas in this block of flats in Ronan Point collapsed, right? So this gave rise to the concept of structural robustness. This was in 1968. In 1972, there was a British code of practice called Code of Practice 110, Design of Concrete Structures. And there is a very nice statement that I will quote from there. It says, no structure can be expected to be resistant to the excessive loads or forces that could arise due to an extreme cause. But it should not be damaged to an extent disproportionate to the original cause. So how that is worked out in each case is left to each individual engineer, but there are guidelines given in codes of practice. So the question I asked myself after doing this inspection is there anything that we can learn from this failure? Now, I have written this up in the structural engineer, that is the reference given at the bottom here. Now, if you think about this load carrying chain, so you have the roofing sheets that carry whatever load is there. I mean, the roof, the weight of the sheet itself, even the weight of the cement dust that was not supposed to be there. It is carrying the load onto these purlins, and it is the purlins that transfer the load onto the girder. And then the girder, when it fails, it should preferably fail in flexure before it fails in shear, because flexural failure is a more gradual form of failure. But even before that, it is much more preferable when there was 6 inches of cement dust if the roofing sheets failed first. If there was just one roofing sheet that failed, it would have been a very manageable and easy failure to manage. Now, there are some calculations that one has to do in this regard, and it means that you have to think about when you are designing any structural element, you have to set not only a lower limit, it should exceed a certain capacity, but it should have an upper limit as well, right? So designing structures like this is not mainstream. I have to confess that I have not been able to make any kind of impact like this Ronan point collapse did on the design philosophy of the day, a design philosophy that is used to this day, the design philosophy of robustness. But this is something that we can think about, because there are many other examples also. When I first presented this many years ago to a meeting of the Society of Structural Engineers, I think it was Dr. Viswalingam who gave the example of fixing a window. So if you look at these multi-story buildings, you have a window that is fitted to the curtain walling or whatever it is. And then if you have an unexpectedly high gust of wind, one would prefer to have the window pane actually fracturing or breaking away from the frame, rather than having the entire frame getting dislodged from the wall. Because it is better to restrict the failure to a member that is higher up in the load carrying chain. So this is my little contribution to design philosophy. A lot of these ideas I have put in this book that the chairman of the Civil Engineering Sectional Committee was kind enough to mention. Philosophy for Engineering, Practice, Context, Ethics, Models and Failure. This has been published by Springer at the end of last year. One other example from that with regard to design context, and there is a research project currently underway with University of College London, together with colleagues from Peradeniya University and Southeastern University as well, looking at the robustness of these school buildings. So this image is taken from something that the Society of Structural Engineers produced soon after the tsunami. Now, most multi-story buildings did not collapse after the tsunami. It was just single-story buildings that got washed off their foundations. The reason is multi-story buildings, they have weight that resists the tsunami loads, and also frame structures like this. But there were a few examples in school buildings. Now, school buildings are characterized by 2 rows of columns like this. So the problem with the tsunami was that it undermined this foundation, because these were on sandy soil. The entire foundation got exposed. So if you expose both this foundation and this foundation, then that bay of the school building will collapse, right? So what we proposed was that perhaps, for school buildings in coastal areas, then one should have a new column like this. So that's perhaps a failure in design context. Nothing majorly wrong with the school building structure itself, but not fit for its context in a situation where you can have storm surges and tsunamis undermining foundations. So that brings me to the last slide, and I have to stop that. How do I? Yes, okay. So this slide is about the way that we can learn from each other's disciplines. It arises out of my reflections in my membership at the National Academy of Sciences, Sri Lanka. So Dr. Kulasinghe was also president, and like I said, I am the current president. Now, we talk a lot about, operating in silos, or rather not operating in silos, listening to each other's disciplines, being multidisciplinary. Dr. Kulasinghe himself was qualified as both as civil and mechanical engineer, and I'm sure he talked about many other areas as well, chemical engineering in his biogas and stuff like that. But my little contribution to interdisciplinarity is what I feel is through exploring this role of analogy. So I will just give you a piece of work which once again is Ronanakar was involved in, and this has to do with the distributions, the statistical distributions. Now, if you look at these statistical distributions, so this is what we call a normal distribution, and the mean of this normal distribution is 0. Now, if you take another distribution of the same area, you can have a different distribution, and the difference between these 2 distributions is that they will have different standard deviations, right? They have the same mean. So the mean is obtained from what we call the first moment of area. The standard deviation is obtained from what we call the second moment of area. Now there are third and fourth moments of area also in this statistical distribution. So this is called the coefficient of skewness, and this is called the coefficient of kurtosis. Now I teach first year mechanics classes and I teach some of these things, but I only confine myself to these first two distributions, because after all, every young civil engineer is taught this equation: F equals m upon I multiplied by y. I is the second moment of area, F is the bending stress, m is the bending moment, and y is the distance to the centroid. So the centroid has to do with the first moment of area. The second moment of area is down here in the denominator. Now the question I asked myself was, okay, if we have first and second moments of area contributing to structural mechanics, would the third and fourth moments of area also contribute in some way to structural mechanics? So it's a exploratory question. It is done purely because of an interest in exploring things, right? So as it happens, we think that the third and fourth moments of area are able to tell us something now. So this has to do with the elastic range of behavior. So this particular equation will hold in this region of what we call m theta curve. So this is the bending moment and this is the rotation. So in the elastic region, we find that this equation will hold. We have the first moment of area and second moment of area. Now, with the onset of plasticity, in other words, when this gets bent, then you have the moment increasing like this and then reducing in this way as well. The difference between this angle of rotation and that angle of rotation is called the rotation capacity, right? So if we take this standardized third moment of area of section given by this equation and the rotation capacity, so these can be calculated for various sections. These are obtained from the literature. So this was purely a literature-oriented inquiry. We find that they nicely fit on a straight line and they are better able to explain rotation capacity than many of the equations that are available. Okay? Similarly, so this is for I sections like this. These are called I sections because they look like a capital I. So similarly, if you look at the fourth moment of area, the standardized fourth moment of area is called kurtosis. In this case, we do not use kurtosis directly, but we use what is called excess kurtosis, which is the difference between kurtosis of the section and a standardized kurtosis defined by this equation in this kind of way. So if we have this normalized excess kurtosis, and once again we look at the literature, here of course in the literature we have both numerical experiments as well as physical experiments to calculate what the rotation capacity is. And here the scatter is greater admittedly than you would find for this third moment of area, but nevertheless we get a line that fits with an R squared value of 0.88, and we can see that there is some kind of relationship between this normalized excess kurtosis and the rotation capacity, in this case not for I sections but for closed sections like this. And as it happens, if you look at different types of closed sections, here you have closed circular hollow sections, here you have rectangular or square hollow sections, and here you have elliptical hollow sections. They all fall on different straight lines like this with different slopes, and this kind of graded behavior from a circular hollow section to a rectangular hollow section. If the aspect ratio of your elliptical hollow section is low, then it is behaving closer to a circular hollow section. If your aspect ratio is high, it behaves closer to a rectangular hollow section, right? So this is also some of the more recent work that we have done, trying to learn from analogy, trying to discover the role of analogy and see how analogy can help us to cross bridges between disciplines. In this case, the discipline of statistics and that of structural mechanics, right? So I will end this lecture. I'm sure there are a lot of younger members also listening to me, and I will end with two quotes. T.Y. Lynn's well-known text on pre-stress concrete is dedicated to engineers who, rather than blindly following the codes of practice, seek to apply the laws of nature. Now, this quote is actually there in that first volume that the president said would be available in 1 week from today, the first volume of the Kulasinghe memoirs. And the editor of that felicitation volume, past President Engineer D.L.O. Mendes, who very kindly contacted me over the last few days with a lot of information. In that volume, he speculates as to whether T.Y. Lin would have had the young Kulasinghe in mind, because he had actually met Dr. Kulasinghe at some conference. So that is also something that I would like to maybe pass on to younger members, to seek to apply the laws of nature rather than blindly following the codes of practice. Now, another thing that Engineer D.L.O. Mendes says, and I must mention this also, that particular book that I mentioned, that I wrote about philosophy for engineering, that is actually being reviewed by Professor Carl Mitcham. And Professor Carl Mitcham is also a person who has written the forward to the second Kulasinghe volume that Engineer D.L.O. Mendes is working on. So there's another small connection with Dr. Kulasinghe. But for this kind of work, for this kind of speculative work, I'm not sure how many people would be interested in this kind of speculative work, but I think speculative work is also important as at least a part of the career of a young academic. So let me quote George Polya, a Hungarian mathematician. He says, "A serious student of mathematics intending to make it his life's work must learn demonstrative reasoning. It is his profession and the distinctive part of his science." Demonstrative reasoning means proving carefully by logic and force of argument. Yet for real success, he must also learn plausible reasoning. This is the kind of reasoning on which his creative work will depend. So this kind of exploratory reasoning. And I think looking for analogies between different disciplines is perhaps one way that we can promote greater collaboration between disciplines. So I will end there with this slide. One more slide. Okay, right. So once again, I would like to thank the Civil Engineering Sectional Committee of the Institution of Engineers and all of these other various institutions and people who have had various influence on my life and career. Some of them collaborators in the research that was presented, some of them who have just encouraged me or been my role models. I would like to mention especially the structures group at Moratuwa University, which has fostered the art and science of structural engineering for many years. And lastly, perhaps I would like to mention, Professor Samatha Hettiarachchi, the late Professor Samatha Hettiarachchi, whose career was very closely connected with mine right from my school days, and his wife Premini. Then also the members of my family, my wife Shanti, who is here, Ashwin and Sanjit, without whom none of this is possible. So thank you very much.
Thank you very much, Professor Priyandas, for your very informative speech. I think most of our young engineers and senior engineers would have gained a lot out of it. In appreciation of your contribution today, I cordially invite Professor Ranjit Disana to give away a token of appreciation to Professor Priyandas. Thank you very much, Professor Disanayake. We have more than 165 participants at this event at this moment. I think it would have gone beyond that earlier. To wind up the session, now I cordially invite Professor Ranjit Disanayake to deliver the vote of thanks.
Very good evening to you all again. The ladies and gentlemen, those who are present here and those who are online here today. Our guest speaker, Engineer Professor Priyan Dias, President IESL, Engineer Professor Sarath Bekong, President-elect IESL, Engineer Darren Pal, past President and CEO of the IESL, and the ladies and gentlemen. Ladies and gentlemen, it's a great privilege that I have been asked to propose the vote of thanks for the Dr. A.N.S. Kulasinghe Memorial Lecture 2020 to commemorate the innovator as a man whose contribution to the field of engineering and engineering education is immense. Dr. A.N.S. Kulasinghe was the pioneer of concrete technology in Sri Lanka. His tireless effort results in establishing the many organizations such as State Engineering Corporation, CECP, NERD, and a few other organizations. On behalf of Civil Engineering Section Committee of IESL, let me thank Engineer Professor Priyan Dias for gracing this occasion to deliver the guest lecture and his finding on the opinion on extending the some Kulasinghe's innovation. Also, I would like to take this opportunity to place our record of heartiest thanks to the IESL for perfect logistic arrangement, guidance they extend to all of us to this year's the Kulasinghe Memorial Lecture with present situation of the country. I can thank everyone for their involvement, for their willingness to take the completion of this task beyond their comfort zone during this quiet situation. Ladies and gentlemen, last but not least, I thank all of you taking extra effort to be online and making this even more colorful. Thank you very much. Have a pleasant evening ahead. Enjoy the rest of the day. Thank you.